This journey you are about to start with me is our lecture on section 6.3.2 regarding the electron acceptors and p-doping. So essentially what we're doing here is that we are repeating the process we just did for the n-type doped semiconductors, and now we will consider so-called p-type doped semiconductors. So in a nutshell, we will show how intentional addition of this time trivalent elements, not pentavalent elements anymore, into the silicon lattice, we can dramatically increase the number of holes in the valence band. So instead of adding pentavalent elements, we are adding trivalent elements, and what's then happening subsequently is that we are now able to change the number of holes in the valence band. And subsequently, these impurity atoms we are adding will be called acceptors because they accept electrons from the silicon lattice. And this is essentially the same thing that we just did in the previous lecture. So please just enjoy the ride, and I will try to be my best to be a quick in treatment. So we will consider here impurity atoms that actually have a lower valency than the host semiconductor. And this is how you generalize the approach also away from silicon. So that if the valency of your host semiconductor changes, this is how you should also change the dopant atoms also. You just lower the valency. And what we will have now, if you would consider silicon and we would doping with a trivalent elements, what we get out is that we end up with an electron vacancy. So in essence, we will end up with a hole that is created in the valence band, into the valence band. And because these impurity atoms, these dopants we are placing inside our semiconductor matrix, because they actually accept an electron, this is then why they are being called as acceptors. And this type of doping, it's called as p-doping because we are changing the concentration of holes. So holes and their concentration is usually denoted with the letter p. And here, this is a picture that highlights what happens and elucidates to you what happens. So we are, for example, considering again silicon lattice. And please note, silicon, of course, forms into a diamond lattice. So FCC lattice, which has two silicon atoms inside the bases. And we add aluminum into the mix every here and there. We dope it slightly, and what happens is that at the end of the accommodation of aluminum into the silicon lattice, we will have positive holes nearby somewhere that can readily move around. So basically these holes will be residing in the valence band. Oops. Let me try to get that console out. Yes, I was able to do it. Okay, so let's now proceed with the calculation. So here, for simplicity, we only consider doping of silicon and only the p-type doping of silicon. And how we do that is that we just reduce the valency by 1. So now we consider trivalent elements. And like the picture already spoils the fun, we are here mainly considering aluminum, but other possibilities would be boron, gallium, or indium as an examples of dopants. And here what happens is that we will be creating an additional hole state into the valence band. And how this process happens, that's highlighted in the picture in B. So in a way we are making an impurity state that is somewhere in energy a little bit higher than the highest energy value of the valence band. And since this state can actually easily accept one electron, it seems to be like a hole state in here. And here the thermal energy will essentially will like excite an electron into this acceptor state, and then subsequently we will have a hole state in the valence band. So this is the process, and what we want to calculate here this time, we want to calculate the kind of let's call this an effective ionization energy associated with this acceptor state. So I don't know. I guess ionization energy is not the best term to describe what happens here, because like in a way this is just accepting an electron, so like in a way nothing is being ionized. But on the other hand, the process is analogous to the case where we were considering a donor state, and there the electron was actually being ionized in a way into the conduction band. So let me call this process as an effective ionization, and let's now try to calculate this effective ionization energy associated with these acceptors. So we want to calculate what is this energy EA, because that provides us means to then calculate what will be the change in the concentration of whole states at the valence band. And again, we will use the Bohr's model, the hydrogen model, and we will just tweak it to be able to give us an estimate where we in fact have an aluminum atom, and that will be residing inside a silicon lattice. And here, please note, in case you're not already familiar with the kind of behavior of holes in these energy diagrams, holes sink when they gain energy. So this is what happens. So I guess in a way you could see that this what we are calculating here is that we are calculating the ionization energy of a whole state. So that when hole would gain energy, then it would actually sink lower into the valence band. And I do not repeat the actual calculation. You can just look at the equations from the previous lecture and from our booklet. But the ionization energies, EAs, are essentially the same for these acceptors than we had the ionization energies, EDs, for a case of donors, so for the case of n-type doped semiconductors. And here what happens is that then now these holes that we have, they are thermally excited already quite easily at the room temperatures. Please remember the kPt value for a room temperature is 26 millielectron volts. And this then means that we will increase the number of whole states in the valence band, and then of course they can readily participate in the electrical conductivity in a macroscopic scale. So conductivity of our semiconductor can also be modified by this kind of p-type doping. Why in practice, like it's not just a matter of taste to be dope by n or p-type doping, is that we are totally neglecting the changes that we will make into the semiconductor's other properties besides the electrical conductivity. And this is in fact more important when we are like trying to make really semiconductor devices, and when we are really trying to decide what kind of doping to actually make. So let me just try to clarify here, and this is slightly beyond our scope because we are more interested in solid state physics, and here we are quite quickly going more towards the kind of field of engineering. So let me just clarify shortly. So if you would be wanting to make semiconductor components, so electronic components, for example, like a diode or a photovoltaic cell or a transistor based on semiconductors, essentially we would be wanting to make a junction or a device known as a PN junction. And here in these kind of junctions, how they operate, like essentially, like we want to control the Fermi levels, because if we can really adjust the position of the Fermi level in our piece of a semiconductor, and then when we can merge two differently behaving semiconductor blocks together, then we can control how easily or how hard it will be for electrons to move from the part A to the part B. So in essence, like when we want to make PN junctions, and subsequently when we want to make more complicated structures, so for example, if we would want to make transistors, and if you want to make a transistor based on PN junctions and semiconductors, we could do so by just adding another layer into the mix. So we could make PNP junctions or NPN junctions, and together these would act as transistors. So this is the kind of case where we really want to consider what kind of doping we would make. So if you want to make a PN junction, as the name suggests, we need a block of semiconductor, a small piece of semiconductor that is p-type doped, And next to that, we need a volume that is n-type doped. And together, these two blocks of semiconducting material can form a p-n junction. And then depending on what do we do with it, the device behaves differently. So we can, for example, we can form a diode using such p-n junction. So basically, electrical current can only flow through one direction through the system and cannot flow the other way around. So basically, it can be used to rectify currents, or one can even make a photodiode so that if light is being shined into this p-n junction, photons are being absorbed near the p-n region, and because of absorption, for example, some electrons are lifted from their valence band into the conduction band, and there they can readily move through the junction and then give rise to a macroscopic electrical current. So in essence, we can make a photovoltaic cell, or we can make a photodiode, a light detecting device using semiconductors. Or other possibilities that you can have with these different types of semiconductor junctions. But like I said already before, this kind of subtlety or complexity is beyond our scope. So our focus here in this course is really on the microscopic properties, so really on the kind of solid state physics of things. And if we would be considering p-n junctions, transistors, and so forth, this is more like an engineering feat. So we do not do that in our course. But if you're interested, please knock yourself out, for example, with the material from our earlier course. So the structure of matter, for example, will be treating semiconductors quite thoroughly. So in essence, we have one chapter devoted on semiconductors in that course. And also we have other courses like really focusing on semiconductors. So for example, the course on semiconductor physics might be a very good course for you to kind of get a better understanding what's happening in terms of doping and why that is being actually done in semiconductor industry. But this is nevertheless like what I wanted to say here. So I just repeat it simply, the fact that we can dope semiconductors by also these kind of acceptors. And what happens then is that we can change now the concentration of whole states at the valence band. And if we can do that, then we can really change the electrical properties of the semiconductor. And then in the kind of like reality, what really makes an impact or has made an impact in our society is the fact that with these different types of junctions, we can in fact make p-n junctions. And when we can make p-n junctions, we can make very small and energy efficient electrical components. So for example, we can make diodes, we can make transistors that are very small, and that kind of components cannot be easily done by other means. So this is what I wanted to say during this lecture. Thanks for listening all the way down, and let's next go and generalize our treatment to the case that we are having both types of doping possibly present in our semiconductor. But more on that in the next lecture. So thanks and bye-bye.